All right, dude, we are live. What's up, guys? This is Dem Keys, and today we are gonna be, uh, we're probably just gonna be chatting about some stuff for maybe an hour and 15 minutes. I kind of started the stream late because earlier I was busy doing some stuff, um, some stuff that just could not be delayed any further. Um, and yeah, that kind of kept me busy and then yeah, stuff happened, so I wasn't able to start the stream on time, and I didn't want to miss a stream because we've got a pretty good, what do you call it, a pretty good streak going where I'm streaming every day, if not almost every day. um, so I kind of wanted to keep that going as long as possible. So I decided that even though I don't necessarily have anything specific that I want to, research on today or focus on today, what we could do is I could chat about some of the research that I've been doing in ESP32 development. Actually, speaking of ESP32 development, this reminded me of something that I had to. Oh, by the way, yeah, this list, man, I love this dimming thing. I mentioned this yesterday as well. I'm loving this dimming thing that I've enabled, and this is just like it's there. It's from one of the plugins in NeoVim, in LazyVim specifically. If you install LazyVim, it usually comes with a bunch of plugins. It also has something called Lazy Extras, which is a list of plugins that are kind of already registered with LazyVim, and LazyVim knows how to install those plugins. So all you have to do is go into the settings and enable a specific plugin if you want that functionality, and then maybe you might need to restart NeoVim. But for the most part, NeoVim is gonna, or LazyVim is gonna handle. Actually, in this case, it's specifically Lazy. Lazy is the plugin manager. So Lazy is gonna handle all the installation for you. After it installs, maybe you might need to uh, close and reopen NeoVim. And once you've done that, the plugin is there. In this case, I don't think I needed to install this specific plugin. I think this specific one was already enabled by default. Um, I forgot what the plugin was called. So there was, I'd found the repo where this functionality was initially introduced. So the repo where this plugin was initially, developed and released. And at the bottom, the person mentioned something along the lines of, if you're using the Zen plugin, then this is available. So I'm assuming that this plugin, it's somehow it gets its functionality gets added if you enable the Zen plugin, which in my case I have the Zen plugin, because it comes by default with NeoVim, or sorry, with LazyVim. And I'm guessing because of that, I also have the dimming functionality available. I could go and look at the list of um, I could go and take a look at the list of what do you call it? The mini plugin set. And this is like an interesting concept. I don't remember exactly the idea um, surrounding this, but this is like one big plugin family. And then like you can install this, and then you install the specific um, plugins that come under this, and there's like more than I think 20 plugins that are under this for various purposes. So it'll be mini dot this or mini dot that or whatever. Um, yeah, I'm not sure. I'm gonna have to look into this later on. It has to be part of one of these plugins that's loaded. Oh, actually, maybe it's not something, maybe it's not mentioned here because it's like loaded by default. So it's like not, you don't have to explicitly um, enable it. Maybe that's why it's not being mentioned here. I think that might be one of the things. I I feel like I'm gonna get a better idea of this after I move forward with the. Oh wait, that thing crashed. Hold on. Yeah, this thing seems to be crashing a lot today. I don't know. I don't know what the issue is, but yeah, it seems to be having trouble today. Okay. Um. Okay. Yeah, we can close this. And I finished. I finished looking up the prices for all of these things. I did. I forgot what price I'd put here. Did I? No. No. Um. I don't remember exactly what the price was, but yeah, I did note down the price, and it was like within the budget. These two, I don't know if I'm gonna go into either of them. Speaker plus amp module and mic plus mic module. In which case, I mean, I might as well just say mic module because the mic is attached to the entire circuitry. It's not like the mic is separate, like how it would be in the case of a speaker. Um, yeah, I could buy like a couple of these as well because I have been meaning to like get into a little bit of that as well, like um, looking into recording tech, and I wanna see to what extent I'm able to create a simple microphone setup where even the DSP of the incoming signal is done on the ESP32, and then that final result is then pushed to the computer so you can like do whatever you want with that audio. Yeah, that should be an interesting project. Yeah, okay. There was something else I wanted to look into. Let's open up a new Gemini instance here, and then I can ask that question because I've been wondering about this. Because after doing some research, actually, yeah, okay, this reminds me. Um, Hold on, what is going on here? Why is this not loading properly? Yeah, give me a second. Oh, oh, I had TikTok open. Yeah, give me a second here. Let me open up my stream. And yeah, we are good. Okay, so here's what I was wondering, right? First of all, what I've been what I what's one of the words? What is one of the things that I was doing research on yesterday? Yesterday, I was doing research on the ESP32S 3, I think it's called. I think so. ESP32S3. Now, I don't know about like all of the features of the ESP32S3 chip, but one of the very important features that I am interested in is the ability for it to do vectorized operations. So apparently, it includes a 128-bit wide register, and there's also a 128-bit data bus, and um, it has essentially vector instructions, SIMD kind of instructions. SIMD instructions are a single instruction, multiple data, basically meaning that one instruction can operate on multiple pieces of data. Now, I didn't fully understand because like I've come across this concept in the past, and I kind of understood like on a higher level that, oh, this means that one instruction is able to operate on multiple pieces of data, but I didn't fully understand exactly what that meant on a lower level, because my assumption was that it would be treated as if it's like multiple um, instructions. But technically, that's still what's happening, but not really. My assumption was that the data would be in different locations. Here, um, and I mean, that could still be the case. I don't know. I'm going to have to see on x86 processors what the situation is, how vector operations are handled, how vector instructions are handled. But at least on the Extensa CPU that supports vector instructions, Gemini explained that the way that it works is you have this 128-bit wide register, and when it's a vector operation, if the data is aligned properly and it can actually be split up into, um, let's say, okay, 128 bits, right? Let's say if we are talking about 16-bit values, that would be 16, 32, and then 64 would be 4, and then 120. So we would be talking about eight 16-bit values, and if we go for 32-bit values, then it would be maybe 4. And if we go lower, like 8-bit values, then we'll have a higher number of values that we can operate on. But the point is, all of these values can be stored into the register, and then that vector instruction, I'm not sure what to call it. But yeah, the SIMD instruction can operate on all the values in that register. And then that data is returned after the results arrive. So this is how apparently they do vectorized operations, vector instructions. I've done assembly in the past, but I never actually went into the vector side of things. So I haven't really explored any of that. I would love to go into that, but like assembly is just not something that I do much these days. I explored it back when I was learning CPU architecture and trying to understand CPU architecture and how programs work and OS architecture and all of that stuff. I did explore it when I was learning this stuff, but after that, I haven't really touched it much, mostly because I haven't had any practical uses for it. I would still recommend people, learn it because it teaches you a lot. I didn't fully understand what 8-bit or 16-bit or 32-bit values actually meant until I looked into assembly. There's so many things that I didn't understand until I looked into assembly. There are so many higher level programming concepts that I didn't understand, or let's say little details within higher level programming that are implemented on a lower level that I didn't fully understand until I explored assembly. So I would still recommend people, explore it at least a little bit, even if it's through the use of like emulators and stuff. Like in my case, I was writing the assembly and compiling it to an ELF binary so it can be run on on Linux directly. But I'm sure there are maybe easier ways to learn and practice x86 assembly within a sort of environment now. I just didn't take that path, but I'm sure there might be easier ways to explore it now. I would definitely recommend people do explore it because it teaches you quite a bit. Like if you are trying to get into programming, learning about this is gonna it's gonna be helpful because there's various concepts that mainly only get implemented on the assembly level that you're not really gonna know about um, if you're just sticking with higher level languages. You don't have to stick with assembly, kind of like how I didn't stick with assembly. But like if you do go on, if you do come down to the lower level, and you're working on like various types of optimizations, or if you end up working on compiler tech and stuff like that, then maybe you'll come back to assembly. Maybe not exactly x86 assembly. It might be a different type of assembly. Like maybe you might be looking into LLVM IR or something else. But yeah, anyways, I'm just going in circles. The point is, I found out that the ESP32S3 processor has support for vector operations. So it's not just called an IoT device; it's called an AIoT device. The idea there is that they're saying that it can be used for artificial intelligence related operations, and that's because a bunch of different neural network related tasks they involve vectorized operations in some way, shape, or form, or they involve operations that could benefit from vectorization in some way, shape, or form. Because if the processor is able to work on an entire chunk of data, like multiple values, all within one instruction, that would definitely be faster than it having to use a separate instruction for each of those values. It's definitely going to be a lot faster. So this is great. This is great news for AI, embedded AI tech, and I'm considering ordering one of those for myself. I also discovered something about like I realized this when Gemini was giving me like examples of code that I would be using, because I was wondering like, okay, on the higher level, if I'm using Rust, on the higher level, how exactly am I specifying that this operation needs to be vectorized? Now, there there are a lot of situations, especially with something like Rust, there are a lot of situations where the compiler is it's clever enough to recognize a certain pattern in your code and apply certain optimizations by itself. There are also times where you might apply a certain logic, and that logic just gets optimized away, as they call it, um, because the compiler thinks it has a better way, and usually it does. The compiler does have a better way of doing what you are trying to do, a much more efficient or faster way of doing what you are trying to do. So internally, it's gonna like just it's gonna implement the logic that you were trying to implement, but in its own more more performance friendly way, more efficient way. So um, there it is possible that those vectorization operations, those vector instructions, they might just get implemented by default. But I was just wondering, like, okay, on the Rust level, how do I specify that this is what I want? Apparently, words. My voice is cracking. I don't know. I don't know why that is. Okay. Apparently, um, there's an attribute for aligning the data to like 16-bit boundaries, and that's something that you would use specifically for data that is meant for this purpose, at least according to Gemini. And that was interesting to me because I mean, I'm still very new to ESP32 Rust development, but I didn't know that, this kind of an attribute existed. So I was like, maybe I should do some research on, these various little details uh, that, because like there might be plenty of other such um, things that I might not know about within the ESP32 Rust ecosystem. So that's one thing, right? I need to do research on those things. Another thing that I was wondering, and that's actually where Gemini comes in again. In this case, I don't think I need to use. Oh, wait, there might be a Google search might be necessary. Hey, so I've been doing a bunch of ESP32 Rust research, learning how to program um, the ESP32 using Rust. I recently discovered that ESP32S3 apparently supports vector, or let me just say SIMD instructions, and is called AIoT, not just IoT, meaning it is intended to help with AI related calculations. This got me wondering something. Currently, we have powerful computer processors, x86 underscore 64, and we have powerful mobile processors, ARM. I think Raspberry Pi also uses ARM. I don't remember. These CPUs usually have multiple cores and have speeds in the gigahertz. So needless to say, they're quite fast. Microcontrollers, on the other hand, just a second. Give me a second here. Okay, so sorry, I just had to crash Firefox on one of my other systems so I could reload it, and hopefully then it's gonna wait, does it need to be updated? Should I leave it alone for some time? I think so. Yeah, it's been talking about the update, so let it do its update. Okay, yeah. Oh, let me finish writing this question. Microcontrollers, on the other hand, are much cheaper, but also much less powerful. They have a smaller amount of RAM and also lesser core speed. Um, what I'm wondering is, in terms of robotics development, how much, how do I say this? Okay, how much focus is being put on computer and mobile CPUs versus microcontroller CPUs? I I'm very much interested. I don't know if this is going to bias the answer, but yeah, let me just put it out there. I'm very much interested in robotics, and I plan, well, robotics and deep learning in general, and I plan on exploring um, the use of micro microcontrollers, microcontrollers for the use of microcontrollers in these fields through embedded programming. So I guess what I'm wondering is, the answer to this is probably yes, but like, hey, getting a bit of reassurance isn't really a bad thing. So I guess what I'm wondering is it worth um, putting the time and effort into this path, into the microcontroller side, if I want to explore robotics and deep learning in general. I should mention I'm aware that a lot of deep learning tasks are aimed at computers, preferably with GPUs. But I very much want to explore deep learning on microcontrollers. Did I spell that wrong? Yeah. Okay, so there's probably going to be like a Google search involved there. In the meantime, let me restart Firefox on my other machine where I had to close it. Also, I guess let me hydrate while the response comes. Okay, all right. We are getting a pretty decent response here. Embedded systems. I guess that's the word I was looking, because I wanted to use the term embedded, but I wasn't sure what the next word is supposed to be. Because I was going to be like embedded devices, embedded microcontrollers, but then I wasn't sure like that didn't make sense. Embedded systems. That's the word I was trying to use. That's the term that I was trying to use. Um, okay, that's an excellent and very insightful question. You've correctly identified a major trend in both the AI and embedded systems worlds. The short answer is yes, it is absolutely worth your time and effort. Your intuition is spot on. Investing in deep learning in deep learning on microcontrollers is a fantastic move for anyone interested in robotics. Here's the breakdown of why addressing your points about powerful CPUs versus microcontrollers in robotics. The two brains of a modern robot. Okay, this is interesting. Most sophisticated robots don't rely on a single type of processor. They use a distributed computing architecture, often with two distinct levels. The high level, the brain, which uses a CPU and GPU. Um, the hardware, this is typically, hold on, let me just make sure you guys are able to see this and things are not stuck. Hold on. What is being shown? Oh, okay. Great. Right. Did this disconnect? This disconnected. Right. Give me a second here. Give me a second here. I'm glad that I caught this earlier. Um, okay. Right. Give me a second. Is it temp rust? Yes, it's temp rust. Okay. So, um, right. Where was I? Yeah. So, hardware. This is typically a powerful single board computer like an NVIDIA Jetson, a Raspberry Pi 5, or an Intel NUC. What is that? Is that Intel's own like system on a board? Hold on for a second here. Yeah, it's like a mini PC. That's interesting. And how much does this cost? It's also not that expensive. Yeah, that's holy shit, dude. I didn't know about this. I knew about the concept of mini PCs and I had seen a mini PC a while back. Actually, this was like a decade back. And that was really interesting to me at the time. This was a Linux meetup that I had gone to, and one of the people there was showing this mini PC thing, and it was really interesting seeing that hey, this small thing, it's also able to be used. Well, it's not also, it is, it's meant for that purpose. It's able to be used as a PC, and as long as you have the right kind of software, you can actually use this in a very optimized way, in a very performance friendly way. Okay, I'm a bit confused about what's going on this other system because specifically the web pages don't seem to be loading that well, but also tabs seem to be like I don't know, malfunctioning. I'm not sure what term to use. Anyways, yeah, okay. Let's continue reading this. Where was I? Yeah, running a full-fledged operating system, usually Linux. Okay, the tasks. It handles the heavy computational load. This is where you run things like SLAM, which is simultaneous localization and mapping. Okay, building a map of the environment and tracking the robot's position within it, then complex path planning, calculating the optimal route from A to B while avoiding obstacles, advanced computer vision, recognizing and classifying many different objects, people, or scenes from a high resolution camera, running large language or decision models, making strategic choices about what to do next. Then the second part is a low level nervous system, which is microcontrollers. The hardware is basically ESP. We were doing Circuit Python, and that's more or less the same thing. Like the idea is to be able to run Python on these microcontrollers. And this person had their own project set up um, for this purpose, and they were using microcontrollers for that. Where was I going with this? Yeah, I'd heard about Teensy around the same time I'd heard about AT Tiny. That was also a thing, AT Tiny. I actually remember ordering a couple of AT Tinies, which I just never used them. Fortunately, they were cheap. Uh, but at some point, maybe I should look into trying to use them as well. Or actually, I don't know. Okay, AT Tiny 85. Let me look it up because it was specifically this. It was specifically an AT Tiny 85. Um, Let me see if there's any way to run, because there's going to be another issue is that there has to be like, you need a tool chain, right? In this case, there's a Rust tool chain involved, which fortunately is being supported by Espressif, who are the developers of who are the manufacturers of ESP32. um for, for AT Tiny, I'm not sure what the situation is. Let me see. AT Tiny Rust AT Tiny example, a quick and dirty example of using Rust to target the AT Tiny 85 microcontroller. It is possible to program the AT Tiny 85 microcontroller using Rust, primarily through the community maintained AVR HAL and AVR device crates. Okay. This requires a specific development environment setup and is considered a more advanced bare metal approach compared to the standard C/Arduino method. Okay, bare metal, no STD. I was about to say Neo STD. Okay. Um, yeah, great. Okay, so we are pretty much going to be doing the same thing that we are doing in the case of ESP32, especially because I'm using no STD. I'm doing bare metal anyways. AT Tiny 85 does not have native USB support, so you'll need an external programmer. Okay, that's where it gets a tiny bit complicated because this is a lot older. I'm talking about like, dude, this must be easily 5+ years old. More, maybe. More. I'm pretty sure I'd ordered these shit, dude. This might have been like 8 years ago. I don't remember. I'm pretty sure I'd ordered these pre-COVID. Like this was before COVID. So I don't know if these microcontrollers would have something like UART to or USB to UART. I don't think if that is being handled. So I mean they do have a USB port. So it's possible maybe it's being handled, or maybe you still need an external programmer. Maybe that USB port doesn't necessarily, translate to you. Actually, hold on. I don't even know what protocol the AT-Tiny understands. I need to look into that. So maybe it's not even like a USB to UART thing. Maybe something else is required. In which case, if this ends up being a little more complicated than it needs to be, I don't think I'm going to go too deep into it because I already have a bunch of ESP32 microcontrollers um, lying around with which I can do plenty of projects. Those AT-Tiny microcontrollers it's like two of them. It's just two of them. Okay, here's something I could do. Maybe once I get better at AT-Tiny, or once I get better at um, ESP32 development with Rust, through some research, maybe I could try to create a programmer for the AT-Tiny. That would be interesting. That would definitely be interesting. For sure. That would be interesting. So I would be writing the Rust code, and then I would compile it to a binary, and then that binary is going to be flashed onto the AT-Tiny to run. I'm going to have to see what the compiler targets and stuff look like. I'm glad that I'm slowly understanding the whole ecosystem, the whole Rust ecosystem, and the various tools involved and stuff. Like, I would have never thought about compiler targets if I wasn't stepping out of the regular the if I wasn't stepping out of um, STD development, if I wasn't stepping out of PC programming for Rust, I probably wouldn't have ever explored the concept of. I mean, maybe eventually I would have looked into that concept because of multiple different OSs being targeted. Maybe eventually I might have looked into it. I probably wouldn't have looked into different architectures, different CPU architectures, because that plays a role. That plays a role as well. It's not just the OS that determines what the target is going to be. It's the architecture, the CPU architecture, the OS, and also the file format that you want to use. And there was one more thing. I forgot what the fourth one was. But yeah, anyways, let's continue reading this. Where was I? Yeah, a single robot might have a dozen of them. Tasks. They handle everything that needs to be fast, reliable, and real time, like motor control, precisely spinning a wheel, or moving a joint using PWM signals and reading encoder feedback. You cannot tolerate the latency of a non-real time or what? You cannot tolerate the latency of a non-real time OS like Linux for this. Okay. Then sensor readings, polling IMUs like accelerators, gyros, distance sensors, and other signal sensors over I2C, SPI, and or UART. Then executing reflexes. A microcontroller can react to a sensor input like a bumper switch hitting a wall. What's a bumper switch? Hold on, let me look this up. Bumper switch. Okay, it seems like this is something specifically robotics related. Yeah, this is interesting. So I'm guessing it's basically just like it's a sensor in the way that it detects bumps, like it sends in a signal when there's a bump. I don't know if it's similar to like a push button switch. I think it's a tiny bit more sophisticated than that, because there does seem to be circuitry involved. I don't think it's as simple as, a switch getting closed in order to complete the circuit. Actually, yeah, let me type what is a bumper switch. A bumper switch sensor is a simple physical pressure sensor that detects contact, often used in robotics and industrial automation to prevent collisions or trigger actions when a surface is touched, acting like a momentary switch that closes or opens an electric circuit upon physical impact, signaling a digital pressed state like one or low to controlled systems. Oh, okay. So, I mean, is it as simple as just like an open and closed switch? Because there seems to be like circuitry involved for some reason, and that makes me think that it might be a little more than just yeah, that makes me think that this might be a little more than actually, okay, no, I think the circuitry is involved because this push button switch is then sending signals over something. It's sending signals over some kind of protocol or some kind of like communication method um, to the microcontroller. The microcontroller is not just seeing this as a switch, as you know, two wires like connecting together. It's another piece of equipment that's sending either an on signal or an off signal. The physical action completes an internal electrical circuit. Okay, the physical contact. When an external force pushes the bumper, it physically depresses the switch. Then the physical action completes or breaks an internal electrical circuit. Signal to controller. The change in the circuit sends a digital signal to the robot's brain or control system. Then action. The program interprets this signal to stop movement, sound an alarm, or perform another programmed action. Okay, all right. Let's continue reading this. Execute reflexes. A microcontroller can react to a sensor input like a bumper switch hitting a wall in microseconds far faster than the high level brain can do, than the high level brain can. Where deep learning on microcontrollers fits in. The field you're describing is called tiny ML. It's not about replacing the big AI brain. It's about making the nervous system smarter by running small, highly optimized deep learning models, inference only, not training, on MCUs. You can enable intelligent sensing, reduce data bandwidth and latency, and improve power efficiency. Okay, let's take a look at each of these. Uh, Enable intelligent sensing. Instead of just sending raw sensor data to the main CPU, the MCU can process it locally. Okay, yeah, sorry, I zoned out for a second. Instead of just sending raw sensor data to the main CPU, the MCU can process it locally. Keyword spotting. An ESP32 can listen for wake words like "Hey robot" while consuming milliwatts of power. When it hears the word, it wakes up the power-hungry main CPU. This is the smart. This is how smart speakers work. Anomaly detection. An MCU controlling a motor can run a tiny model on vibration data from an accelerometer. It can it can detect if the motor is about to fail and either shut it down or alert the main brain without ever streaming gigabytes of sensor data. Okay? Simple vision. The ESP32S3 is powerful enough for low resolution image classification. A robot could use it for simple person detected or obstacle present trigger to wake the main system instead of having the main camera and GPU running 24/7. Then, reduce data bandwidth and latency. The main CPU The main CPU doesn't need to be burdened with processing every single data point from every single sensor. The MCUs can pre-process the data, look for interesting events, and only send relevant information upstairs. This leads to a more efficient and responsive system. Then improving hold on. I think this thing crashed again. Did it? I'm not sure if it crashed. Yeah, it crashed. I don't know at what point it crashed, but holy shit, this is just not doing well. Um, it's okay. All right. Um, let's go back. Okay. Now, where were we? Yeah, improve power efficiency. This is this is critical for battery-powered robots. Running a tiny model on an MCU that consumes 100 milliwatts is vastly more efficient than running a large model on a GPU that consumes 15 watts, especially for always-on tasks. True, true. Your path forward. Your interest in Rust on ESP32 is a fantastic starting point. The discovery of SIMD instructions on the ESP32 S3 is key. Those are exactly the kind of hardware accelerations that make TinyML feasible. So, is it worth it for a robotics career? 100%. Okay. Um, an engineer who understands both high-level AI, Python, PyTorch, TensorFlow, and low-level real-time systems, Rust, C++ on MCUs, is incredibly valuable. You'd be able to design and build the entire robotic system from the motor controller all the way to the decision-making AI. Actually, that is true. Yeah, I do know both the high-level and the low-level stuff. That is true. And in this case, like one way that I was planning on, uh, I kind of did have something similar in mind, but I wasn't imagining multiple microcontrollers being involved, mostly because I don't have any robotics experience, so I didn't really think about it, that far ahead in terms of the design. But I did have something in mind where it was going to be like, okay, there's a microcontroller, um, and the microcontroller is controlling various components within that circuit. However, it is also connected wirelessly to the computer. So it is currently interacting with a bigger quote unquote brain, which is a Rust program or a Python program or something running on a PC, where we have this constant loop going on where it receives data from the microcontroller, processes the data, and then sends its result back to the microcontroller. So essentially, it was going to be like the computer is the brain, the computer is the big brain, and the microcontroller is still the smaller brain slash brains. I just wasn't imagining, multiple brains, multiple smaller brains being there. I also wasn't imagining, I wasn't imagining it in terms of like, a bigger brain and a smaller brain. I was looking at it from that angle. I think uh more so I was looking at it as the ESP32 is just going to be relaying information back to um relaying information to the computer, and then the computer will process the thing and then send the information back, and then the microcontroller does the controlling. But now I'm thinking maybe I should kind of change that way of thinking, because like this explanation definitely helped kind of put things into perspective. Okay, for a deep learning career, it's a powerful specialization. While most of the industry is focused on massive cloud models, TinyML is a huge and rapidly growing frontier for edge devices, IoT, and robotics. Keep exploring exactly what you are doing. The skills you are building are not a niche distraction. That's good to know. They are at the forefront of creating more efficient, capable, and intelligent autonomous systems. Hell yeah. Got a got a bit of a pep talk from Gemini. But yeah, dude, I'm excited. I do need to add ESP32S3 to my list because I want to explore the vectorized instructions thing. For now, I think I can only afford one because they do seem to be slightly more expensive than the regular ESP32s. I think so. Fortunately, actually, okay, here's the thing, right? Um, Even in ESP32S3, apparently they have super minis. So the way I have ESP32C3 super minis, the same way they have S3 super minis. At least that's what I've seen online. And I was curious about whether those super minis would also support vectorized operations, and it turns out, yeah, they would. So if I go for the smaller ones, the bigger ones would be more expensive, mostly because of, them being bigger. Uh, well, it's not just a size thing. The size allows more stuff, especially stuff like more pins, and there's more circuitry for a bunch of other things. There's also apparently a bigger surface area, a bigger words, a bigger surface area allows for more heat dissipation. So if I'm doing ML stuff or DL stuff uh, on uh, on a microcontroller, having a wider surface area would be a little more beneficial. Though I guess I'll have to test that out. I still haven't. Dude, I'm curious if we can actually get temperature readings. ESP32 temperature, not temperature sensor, ESP32 board temperature. ESP32's built-in temperature sensor. The ESP32 generates a lot of heat itself, so it'll be harder to check what is the current temp in the Oh, no, back up. Hold on. I'm looking for the ESP32's thing itself. Okay, so if we look at this temperature sensor, the ESP32 has a built-in sensor used to measure the chip's internal temperature. That's what I'm looking for. That's what I'm looking for. The temperature sensor module contains an 8-bit sigma delta analog to digital converter and a digital to analog converter to compensate for the temperature measurement. The temperature sensor is designed primarily to measure the temperature inside the silicon. Again, exactly what I'm looking for. The sensor can reflect the temperature changes very well, but it can't give a precise measurement value. So it's not recommended for use. It's not recommended to use it for ambient temperature measurement. Okay. Yeah. I definitely need to look into the temperature thing. Let me ask Gemini one last question. Um, I'm learning ESP32 development with Rust. I'm still very new to ESP32, so I guess you can say I'm also learning ESP32. Um, I I have ESP32, ESP32 Room, ESP32 C3 Super Mini. Um, yeah, and ESP32. Well, okay, I can also add in and ESP 32 can. For the sake of simplicity, we can focus on just the ESP32 and Vroom as well. I'm wondering if there is a way to measure how hot um, the the MCU is getting, and what are some cooling methods I can employ. Because I'm trying to think of where exactly I would stick the heatsink. Well, generally you would stick the heatsink like directly on the chip itself, um, right? But like, holy shit, this is gonna need, because like if you guys see an ESP32 Super Mini, they are not joking about like Super Mini. It is one third of your index finger, and just take two index fingers together if you want to know how wide it is. It's actually slightly lesser than two index fingers. Um, it is small. That thing is tiny. The board is tiny, so the chip on it is even tinier. That thing is small. So in terms of placing um some kind of actually I don't think I don't think it's meant to be used for situations where there's heavy calculations required. That being said, looking at my own ESP32, the only metallic thing that I see on it that we can put a heatsink on is what I'm assuming, and I could be wrong about this assumption because this could actually be where the entire circuitry of the ESP32 chipset is. Um, but like there is, okay, let me show an image of specifically the ESP32 Vroom because that's what I'm currently working with. Give me a second here. ESP32 Vroom. Um, yeah, ESP32 Vroom 32. All right, now while this loads up, I guess I can transition back. No, hold on. Let the loading let the loading finish so I can see what exactly it's. If I can just get a couple of images, that'll be enough to show what I'm talking about. Okay, I can go on images itself. Yeah, okay. So, just a second. Yeah. So if you look here, each of these ESP32, so these are the bigger versions. These are not super minis. They're still small, but these are not super minis. The super minis are like really small. These ESP32s, these are your regular sized dev boards. And each of these, you'll notice they have like a silver kind of thing here. I was, for some reason, assuming that the only thing that that contains is the radio frequency, the RF related circuitry. So Wi-Fi and Bluetooth and anything else wireless that might be supported. For some reason, I was assuming that that's all that's in here, but I'm starting to think that that might not be the case. So let me read this. That's a fantastic collection of boards. Rust and the ESP32 are a powerful combination, though the learning curve for embedded Rust is can be a bit steep because you're managing hardware at a very low level. The good news is that almost all ESP32 variants, including the C3 and the classic Vroom, have a built-in internal temperature sensor measuring temperature in Rust. The internal sensors measure the die temperature, that is the temperature of the silicon chip itself, not the room temperature. This is exactly what you need to see if the MCU is overheating. Yep. How it works in Rust. Um, if you use the ESP HAL, the bare metal hardware abstraction layer, you can access the internal sensor. Here is a conceptual example of you would set it, how you would set it up for a classic ESP32 or a C3. Okay, so there's code being given here. All that is fine. Okay, great. A note on accuracy. For the classic ESP32, the sensor is notorious for having a large offset. It might tell you it's 50 degrees Celsius when it's actually 40 degrees Celsius. You often have to calibrate it in your code. All right. ESP32C3, the sensor on the C3, like your Super Mini, is much more accurate and easier to use than the one on the older Vroom modules. Okay. Why does it get hot? The ESP32 usually runs cool, but two things make it heat up faster. One is Wi-Fi slash Bluetooth. The radio power amplifier generates significant heat, and um, another thing is fast clock speeds running at 240 megahertz. Oh yeah, you can actually set the speed for the processor. I forgot about that. Yeah. Um, Running at 240 megahertz constantly will warm the chip. I should test that out actually. In a safe way. But like, yeah, I should test that out. Poor voltage regulation. On cheap boards, the voltage regulator next to the ESP32 chip can get hot and transfer that heat to the MCU. Then cooling methods. If your project is in a tight enclosure or doing heavy processing, you might need to cool it down. Small heat sinks, thermal pads. Thermal pads. I need to look into what that is. And then active airflow. Oh yeah, okay, we can just have like a fan blowing at it. That works. Yeah. Okay, that works. That's still a possibility. That is definitely a possibility. Yeah. Or we can have a bit of a sophisticated system. We can set up a heat sink along with some thermal paste and just stick that heat sink on the chip thing. Oh, actually, okay. Oh, okay. What I was saying is, we can take a heatsink, stick it on the chip thing, and then use fans to blow at the heatsink. So the heat it gets absorbed into the heatsink and it goes to the fins, and then you can blow fan air at those fins to cool them off. Okay, software cooling. You can lower the clock speed. You can use deep sleep and modem sleep. In Rust, you can tell the Wi-Fi radio to go to sleep between beacons, and oh, this is the number one way to reduce the heat while staying connected. Which board are you currently coding for? If you tell so and so so and so. Okay, I have two questions. On a regular sized ESP32 dev board, where exactly is the MCU? Um, I usually see um, a square, um, a square metal block on the board, but for some reason, I was assuming it's all RF circuitry. Um, in Also on the bigger boards, where exactly am I sticking the heatsink? On the Super Minis, it's an even bigger dilemma because they are really tiny. So where exactly am I sticking the heatsink on those tiny boards? Okay, you've hit on one of the most common points of confusion for beginners. When you look at the ESP32, you aren't usually looking at the chip itself, but rather a module. Okay, where is the MCU on a Vroom board? On a regular sized dev kit Vroom, that square metal block is indeed what you're looking for. However, your assumption wasn't entirely wrong. It's not just the MCU. Under the hood, inside that metal can, called an RF shield, are three main things: the ESP32 silicon die, which is the actual MCU, a flash memory chip, and the RF matching circuitry. The shield's job: it exists primarily to block electromagnetic interference, so the Wi-Fi slash Bluetooth radio doesn't interfere with other electronics and vice versa. Heatsink placement: you can stick the heatsink directly on top of the metal square. Even though there's a tiny air gap between the shield and the chip, the shield is soldered to the grounded plane of the module, which acts as a large heat spreader. All right. The Super Mini dilemma. The ESP32C3 Super Mini is different because it often doesn't use a metal shield to save space. The MCU location. Look for the small black square chip on the top of the board. It's usually about 5 by 5 millimeters. This is the actual ESP32C3 SoC. All right. Heatsink placement. Because it's so tiny, a traditional finned heatsink is often overkill and physically difficult to mount. Option A: if you can find a tiny 5 millimeter copper shim or heatsink, glue it to the top of that black chip with thermal adhesive. Okay. Option B, the pro way. Most most heat on these tiny boards actually escapes through the bottom of the PCB. If you flip the board over, you'll see several tiny gold colored holes, also called vias, directly under where the chip sits. All right. You can actually stick a large heatsink to the back of the board to pull heat through those vias. I didn't know that. Holy shit, dude. I need to take a look at my Super Minis again. Actually, I think maybe I might have seen them at some point in the past, and I just assumed they were like test points or places where you could solder wires on for some debugging purpose or something. I wasn't assuming that it's for cooling purposes. Okay, the secret to cooling ESP32s. If you are running a heavy Rust application like image processing on your ESP32 cam, you'll notice it gets hot fast. Here's the hierarchy of cooling effectiveness. One is airflow, which is the best. Even a tiny bit of moving air, a small 5-volt fan is 10x more effective than a heatsink in a sealed plastic box. Okay, thermal vias, cooling the bottom of the board is often more effective than cooling the metal shield because the chip is directly soldered onto the PCB's copper ground plane. The ESP32 cam trick. On the on the cam module, the camera ribbon cable often sits right over the MCU. If you're adding a heatsink, make sure you aren't cooking the camera cable by trapping heat under it. Okay. All right. Okay. So we are pretty much at our we are pretty much at the end over here, and give me a second. All right, let's see if we are able to even chat in this person's stream. Okay, you know what? I think we can go to this person's stream. Right. So I'm gonna set up the raid, and hopefully they don't have any settings that prevent raids from, you know, one viewer streams. Their name is Jocelyn Schmidt. Yes, okay, we are able to raid. All right, so that's gonna be it for today's stream. Dude, I need to get some proper sleep. And then hopefully tomorrow's stream is gonna be a little more energetic and slightly, earlier than today. Yeah, dude. Um, that's it, I guess. Yeah. That's gonna be it for today's stream. I hope you guys have a nice day, and I'll see you all next time. Peace.